So hi, I'm Rahul, and today we will be talking about Polaris. Polaris enables transaction priority in our optimistic concurrency control protocols. Second, and let's go. Where's my mouse? Okay, so before we go deeper into the nuts and bolts of the protocol, we should go over the introduction where we talk about the general theme. Actually, Polaris needs a lot of introduction because it builds on a lot of founding blocks as we will go over them in the coming slides. But first things first, Polaris is an optimistic concurrency control protocol which supports multiple levels of priority. These priorities can be defined by the user or the system. They can be static or dynamic. Transactions within the same priority group are fully optimistic. They behave as if no reservation or priority existed. The prioritization is accomplished in Polaris via reservation, which we'll talk about in the later parts of the slides. According to the paper, the protocol offers the following benefits: significantly lower P999 tail latencies and higher throughput for high contention workloads. One of the main claims that the author make is when we have optimistic concurrency control algorithms and there's a lot of contentions, the protocol suffers from a lot of aborts because of high contention. But by introducing a little bit of pessimism, they are able to achieve higher throughput for high contention workloads as well. So the first building block that we need to understand is optimistic concurrency control, which I guess everybody must be familiar with. But on a high level, let's go over what does it entail. So the algorithm is divided into three phases: read, validation, and write. The first phase of the protocol is the read phase. It's a concurrent phase where multiple transactions can be executing in parallel. Here we record the version of each data item that we are reading, whether that read is just for read's sake or for mutation later. These versions will be later used during the validation phase. The second phase is the validation phase, and it is executed serially. Here we are verifying to make sure that all the data version that we read for mutations or for reads are the same time or have the same version. If any of the data type or data item has a differing version, that means transaction has been modified while we were executing and we must abort. And the right phase, and the last phase is the write phase, which is also serial. And we take our write block, all the mutations that we have done, and we write it back to the underlying storage. One point to mention is any mutation that we make during the transaction context is kept local within the transaction because as we are making mutations and the transaction is not committed, that means no other transaction is allowed to see the data. So all these mutations remain local to the transaction, and that's how OCC is able to support read your own rights as well. So this is one example of optimistic concurrency control. Here, the time is flowing from top to down, and we can see there are two transactions. I have taken two fields for each data item. .v means version and .d means data. So for example, X is a data item and X.v is X's version and X.d is X data. So as we can see, both the transactions are accessing different data items. Transaction 1 is accessing X and transaction 2 is reading Y or making mutations as well, right? The commit block is shown as a horizontal block which goes through each transaction because it's a global mutual exclusion. So in this scenario, both the transactions are able to commit because they are both acting on a different data set. This is an example where optimistic concurrency control has to fail because we have two transactions, both are reading the same data. The transaction that is first able to acquire the lock or the global mutual exclusion for validation and write is able to commit. So we can see that transaction 1 is able to commit and transaction 2 has to abort because when transaction 2 comes in, its data version will not match because transaction 1 has already written some data to it. The second building block that we need for understanding Polaris is Silo. Silo is an in-memory database designed for modern multi-core machines, which has higher number of processors and a lot of main memory. It's a serializable database. It uses a version of optimistic concurrency control. Why do they say a version? Because in the original paper that was published by Kung in 19 whatnot, they have a global mutual exclusion region. But here, Silo tries to avoid the centralized contention. For example, writes to the main memory are only required during the commit phase. We'll go more into the details, but this is the high level idea of what Silo is. And Silo, Polaris uses Silo, builds on top of Silo, you can say that. So some details. I'm mostly talking about Silo through the lens of Polaris and things that will help us understand the semantics and guarantees of Silo. So Silo is based on time periods called epochs, and each epoch has an epoch number. Epochs are essentially, you can imagine as serialization points within the transaction's history. And for example, if there are two transactions, T1 and T2, T1's epoch is before T2's epoch, then we can say for sure that T1 precedes T2 in the serial order. Essentially, the system does not know the serial order except across the transaction boundaries, epoch boundaries. A dedicated thread is present in the system to periodically increment the epoch number, and this epoch number is visible to all worker threads which are actually handling client requests. All worker threads needs to access this number during commit time. Notice there is one important part. They never update the global epoch number. This is an optimization of the algorithm. All the workers that need to commit, they only read the global epoch, but they never increment it. So that's how Silo is able to like go around the issues of cache invalidations and whatnot just by using fences, because they don't need to update some global variable which every other thread needs to see and whatnot. Silo also introduces a per record field which is called transaction ID. And this transaction ID is composed of two data items. One is called data version and the latch. So the data version we can imagine is the traditional OCC data version, which we have to use during the validation phase. And latch can be a single bit, which is bit is on, we know the record is locked, and bit is off, that means record is not locked. So in a world, you can imagine that if this is a 64-bit field, only one bit is used for latch and rest 63 bits are used for the data version. Now we can start talking about Polaris that makes use of Silo. So instead of using 63 bits for the data version, Polaris uses the same 64 bits to introduce some other information for priorities and reservation as well. They are trying to use the 64 bits so that in most of the architectures, this is a single atomic instruction, but we'll talk about it later as well. So 4 bits are needed for priority version, 4 bits are needed for priority, and 10 bits for a reference counter. Reference counter is essentially to make sure transactions within the same priority group increment and decrement the reference counter. So let's go over the record access protocol. This protocol is used every time you want to read a data item or read a data item from mutation as well, right? So as we can see, there are two for loops or do while loops. From line 2 to 4, we are trying to make sure that the transaction that we read from the record, remember, transaction ID is a per record field. So if you're reading 10 data items, all these 10 items will have the transaction IDs. And all these 10 transaction IDs will have their data version, priority, reservation, all that thing that we already talked about. So line 2 to 4, make sure that the transaction ID that we read from the record is not logged. The lock is the latch is only a single bit. And if it's not logged, we try to reserve the record. As you can see in the slide that line 5 and 6 are blue in color. This is mainly to signify that this is the only place where Polaris differs from the underlying algorithm, which is Silo. So rhythm is the only blue lines of the addition by Polaris. So we make sure that the record is not logged. We try to get using whatever algorithm. We'll come to it later, but today we can just think about like make sure the record is not logged, try to reserve it. And then on line 7, we do a compare and swap to make sure that we can install the new transaction ID, which does not change the version. This is only making sure the reservation information is updated. And from line 1 to 7, a new reservation ID, a new transaction ID will be installed for that record. On line 8, we make sure that the record is added to a read set. All the items, if you think about it, when we read or when we read for mutation, need to be present in the read set, right? Because if you're trying to mutate, you have to read them first. On line 9, we double check, not double check, we check if the read that we made is for write also, so that we add the element to the write set. So algorithm 2 talks about the reservation protocol. And the main goal of the reservation protocol of Polaris is to make sure lower priority transaction should not be able to abort a higher priority transaction. One key point I want to emphasize in this whole presentation is the prioritization part of this algorithm is not for serialization. It's just to make sure to help the algorithm that higher priority transactions have higher chances to succeed and lower than the lower priority transactions. So for example, if A is a higher priority transaction and B is a low priority transaction, and if A has read the record but not committed, that means A has read it but is going to commit it later. So B should not be able to come, which is a low priority transaction, from behind and able to say, hey, I'm trying to write it. Because once B writes it, A will not be able to commit. That means a higher priority transaction was blocked because of a lower priority transaction. On the same lines, if B has the record, has read the record, but not committed, A must be able to come in and say, I don't care, I'm a higher priority transaction, so I will preempt you and make sure I go first. Let's go over the actual algorithm for reservation. It's pretty simple. This algorithm, if you look, does not mutate any of the records. It just tries to create the new transaction ID, and it doesn't even change the data version. So it takes the record, figures out the new priority, and returns back the new transaction ID, which the record access protocol has to go and update it using compare and swap, right? So if we can see that line 3, we make sure that the reservation is by the same priority transaction, that we increase the reference counter. Remember, in the transaction ID field, we have reference counter, priority, and stuff. So if same priority transaction comes in, we just increment the reference counter. If this is a higher priority transaction, then we reset the reference count to 1 and preempt it basically from the lower priority transaction, right? Because we are resetting the priority field. We are also saying reference count is 1 and its result is true, right? Otherwise, if it's a write and if it's a lower priority transaction, then I should not be able to proceed. I should not be able to reserve it. Hence, I need to abort the transaction. So we had the record access protocol, which uses the reservation protocol. And now the last part, which is the commit protocol. And commit protocol, I think it was a little bigger, so I have split it in 2 slides. This is the first part of the slide where we take all the elements in a write set and make sure that they are not reserved by a higher priority transaction. If they are, which on line 4, we check that if it's reserved by a higher priority transaction or the latch bit is on, that means some other transaction of the same group maybe has already taken a lock. That means we cannot go and commit. Hence, we need to abort. And we do this in a while loop. We can see for all the data items in the write set. Once we are able to take locks, as we can see on line 6 and 7, then we do a similar compare and swap to make sure we are able to install the lock bit on. Because once we install the lock bit on, then somebody else cannot come in. Our read access protocol will make sure that somebody should not read that data item. From line 9 to line 14, we can see that we go through all the data items in the read set. We check if the data is not locked and the data version has not been updated. So this is one other critical point, which is for read for write items, we lock using the latch bit. For read items, we make sure that the version that we read is not changed during the commit phase, right? Remember, priority does not take part in serialization. Only data version takes part in serialization. So in read set, we just make sure that is the same version that we read before. If all this passes, that means validation has passed, and we calculate the new version ID using W, the write set. Silo also goes into a little detail of how they calculate the commit transaction ID, which takes the read elements, the write elements, and the epoch number and calculates the maximum, the epoch number that we have not seen and stuff like that. But we can imagine that this black box just generates a data version. For all the items in the read set, for in the write set, we go and install the writes because we have already acquired the latch bit, so nobody will be able to read it and modify it as well. And for all the elements in the read set, we go and clean up their transaction bits. We'll see in a little bit what cleanup means. Write cleanup is pretty simple, where we take the transaction ID, set it to unlock, priority is 0. We set all these stuff and then we are done. We don't have much to do over here. Read cleanup is a little tricky because we have to check for a few things where, for example, in line 2 to 3, we check if the transaction ID is not logged. That means somebody else came from behind and took the item for writing and whatnot. So we don't need to clean up, right? We are already done with it. And for other cases as well, if the priority version does not match, so we need to go and clean up. Otherwise, from line 8 to 10, we just set the reference count to 0 and be done with it. So this is the cleanup part that we have to do after the commit protocol. Priority in Polaris can be assigned statically or dynamically, or it can be user-defined priority, or it can be system-defined. In a lot of experiments, they've used this formula for calculating the priority, which is if the abort count is less than some number t, it will always be assigned P0. P0 in the sense some quantity of priority. It can be 8, 9, or 10. And anytime the number is increases from the initial number, will make sure the abort count is counted in calculating the newer priority. For example, after 8 aborts, for every 3 aborts, we'll increment the priority by 1. So this is how they calculate the priority in this algorithm. So this is the whole algorithm, and we'll go over some of the results that they presented. This first graph is pretty interesting one. So in this experiment, every transaction is assigned a binary priority, 0 for low priority and 1 for high priority. And if we see, the graph has kind of a U shape. So on the left side, they claim that we get the same number of transactions throughput as equal to silo, right? Because there's one tricky part that I haven't mentioned, which is about optimization. For if a transaction has the lowest priority 0, they do not go through the reservation protocol. They think, okay, it's a lowest priority, you don't need to reserve anything. And when it gets aborted multiple times, then it goes to the reservation protocol. So you can imagine in a world where all the transactions are priority 0, they don't go through the blue code that we mentioned. And that means the code is equal to silo. Therefore, the leftmost point of the graph points to the exact same number of transactions that Silo accomplishes. So Polaris and Silo are exactly same when you have all transactions in the 0 priority, essentially behaving like an optimistic concurrency control. When we introduce a little bit of higher priority transactions like 5%, the throughput drops by 6%. And it has the lowest, the U curve has the lowest point when 70% of the transactions are high priority. On the similar vein, we can think that the rightmost part of this graph should be equal to silo, because all priorities are all high. But when all priorities are high, that means the code has to go through reservation, which decreases the throughput. Otherwise, it will be same as silo as well. These are some results for YCSB A workload where we have a read set and the write set of 50-50%. The interesting take I want to emphasize in this graph is that as we increase the number of threads, Polaris and Silo almost behaves same in number of throughput, as we can see in the top left graph, right? The red and the orange graph are almost overlapping each other. But the main difference is in the tail latencies. If you can see in the bottom right graph, as we increase the number of threads, the tail latency of Polaris is way less compared to Silo. And I think this is because of the reservation protocol that they implemented, where certain high number of transactions, which can be the number of times a transaction has been aborted, right, gets priority to execute and hence has lower tail latency. Let's go over some other graphs. This is the graph where the workload is only read. So you can see there is no difference between Solaris and Silo and Polaris. On the top left graph, we can see that on throughput, most of them match, right? Silo and Polaris are almost overlapping. And in tail latencies percentage as well, you can see, and latency as well, as we increase the number of threads, they are almost the same. There's a little bit of, in the bottom left, difference between Silo and Polaris. And I guess this is because of the shared memory they're trying to access. Another graph that I wanted to talk about is TPCC high contention one. The same story here as well. If we can see in the bottom right graph, the latency of Polaris is way better compared to Silo, because during high contention, we're able to reserve and blah, and Silo is not able to, therefore, a lot of transactions can keep on getting aborted again and again. And in low contention, almost behaves the same. Yeah, in low contention, you can see that Polaris and Silo and Polaris almost behave the same. I think that's all.